Good afternoon. It's 4 o'clock in Taiwan, and welcome to this online seminar, which is to be given by Professor Michel Blanc. This is a part of the low-latitude atmospheric research seminar series organized by the low-latitude working group of AOGS, and we have already 9 of them, so this is number 10. And we are very happy to have Michel to give us some information on the important information on the International Meridian Circle Project. We'll hear from him. But let me say that Michel is a very distinguished space scientist, and his work on in 1980 is I would say, a classic monumental contribution to the atmospheric physics, written together with Ray Robo, and which basically laid the foundation of the connection, coupling between the mesosphere and ionosphere, and also from the high latitude ionosphere to the low latitude ionosphere. Therefore, it's of fundamental importance to the space weather study. And for this reason, I think it's also great interest to the low latitude atmospheric research community. And besides the atmospheric research, which Michel started early, he later on, and I met him very first time in a Cassini study team meeting back in 1980, must be 1985 or 84, and he was a very young person, still very young, and then from then on, you know, he kind of switch his attention, some of his attention to planetary science, basically Saturn, Jupiter, and so much so that he has led the proposal team of the ESA JUICE mission, which is on its way to Jupiter to orbit around Ganymede. So it's a fantastic mission, and all because of Michel's contribution. So we are very thankful to Michel for his great contribution. But for now, let's hear what he wants to tell us about the IMCP project. Michel, please.
Thank you very much, Professor Ip. Thank you very much, Wing. It's a great pleasure indeed to address the audience of the low-latitude working group of the AOGS. So this morning for me, it's a great pleasure to address this audience of the low-latitude working group of the AOGS to introduce to you a project called the International Meridian Circle Project. This project has actually been initiated by the Chinese Academy of Sciences, the National Space Science Center, for several years already. And its idea is really to build a global monitoring of the Earth's ionosphere to monitor, let's say, basically all types of natural and anthropic hazards. So I am one of the chief scientists. There is a group of chief scientists, which is led by Professor William Liu, and I will do my best to tell you what we are doing with the IMCP and in which way I think it is extremely relevant for low-latitude regions research. So now a few main references on the IMCP project. I would like to have a few. First, the IMCP is an extension of the Chinese Meridian Project, the CMP, of which you can find a very good description in this article by Shi Wang and collaborators, where there are very nice results about ionospheric science produced by the Chinese part of the system. Now, in terms of description of the International Meridian Circle Project itself, I have put a few references here. Let me say that one of them, the second actually, is a Tycon magazine. So it's a report of an EC Beijing forum that took place in September 2019, just after the pandemic, and which has been released about a year later. I think it's a basic reference, but there is also this article in Science China, which is an international publication giving a description of the project. So let me go to the next slide to tell you about the concept and the science objectives of the IMCP. So the idea, as you see here, is that around the Earth, the ionosphere, which is the conducting part of the upper atmosphere, sort of constitutes a screen on which we can detect many kinds of hazards affecting our environment. And there is many good reasons for that. The ionosphere and the middle upper atmosphere, so what we call the IMUA in the project. The Americans rather say the lower thermosphere and ionosphere, but I think it's the main concept. It is really the boundary layer separating the plasma Earth from the fluid Earth, as we all know. It's a place where we have the maximum deposition of energy coming from above and from below. For several reasons, vertical heat conduction in the thermosphere, it's conducts heat down to the lower ionosphere. Photon, particle, and Joule heating maximize there. And as far as what comes from below, atmospheric waves propagate upwards and break about at this altitude. So the IMUA is really a live TV screen on which we can detect disturbances propagating from above and from below. And this is actually presented in a more quantitative way here. Here you have this description of the Earth system with the solid Earth in black, the fluid Earth in blue, and the plasma Earth, so ionosphere, magnetosphere, in pink. And you see that the lower ionosphere is really the place where plasma Earth and fluid Earth overlap, producing a lot of interesting phenomena that we all know. It's the place where you have the maximum of ionospheric currents and conductances, so therefore Joule heating maximizes at these altitudes. It's a place where solar EUV is absorbed, most of it. It's the place of largest gradient in the neutral densities also, and particle energy deposition. And finally, as I mentioned already, the thermospheric gradient, positive upwards, is such that heat is conducted down to this specific layer, whereas tide and waves are propagating from below and breaking there and depositing energy and momentum there. So you have in this cartoon the presentation of the magnetic field of the Earth in red, and the classical distinction between the different latitude layers. And of course, I would like to mention today the importance of this low latitude region here. It's really a unique place because of the geometry of the magnetic field, which culminates inside the ionosphere. And this makes it a very special region, as we will show later, where plasma motions are essentially expressed vertically as a response to the variations in the electric fields and the electric currents. So that makes all the interest of this region. And the idea is really to use it to detect and study different types of hazards. So on this slide now, you have a description of what the IMUA screen here is capable of detecting and should detect for our interest as scientists. So first, you have, of course, I will call it SW, space weather. So all the solar activities coming through the interplanetary space, interacting with the magnetosphere, in the end, deposit energy into the upper atmosphere. And this happens at all latitudes. And of course, we want to understand how that happens. So space weather is one element, of course, an important one. of the IMCP project. Then there is more. First, we want to study the effects of the atmosphere on the upper atmosphere, the dense atmosphere. So that takes the study of global electric circuits. We know that a fraction of the electricity charges which are produced by storms, thunderstorms, goes through the ionospheric circuit, so feed the global circuit, and also atmospheric waves of different kinds which are produced by, let's say, weather systems, by weather fronts, and so on, propagate upwards, and they break or deposit energy in the same upper atmosphere. So atmospheric science is one of the elements that is of interest to the IMCP. Then there is solid Earth. So solid Earth, of course, influences this IMWA screen in two ways. First, geomagnetic field variations. They are important even at the level of multiple decades, and they really play a role in the way we see changes in our upper atmosphere. But also seismic activity, which is a direct effect of the dynamics of solid Earth, we know have some impact, still not very well understood, on the upper atmosphere, and we want to understand it. Finally, all these components, I mean, the sun, the atmosphere variations, solid Earth effects, solid Earth emissions, contribute to climate change in the global sense. So climate has one of its consequences as a change in the upper atmosphere, and here too, we want to quantify and understand it over time. That means we have to measure for, let's say, decades to understand what happens. So the overarching goal of the IMCP, and I forgot to put all the codes here, is to build a global screen on which to detect, study, and understand the images of the different natural and anthropic disturbances affecting our Earth system, and more particularly the upper atmosphere. So now we'll go in the details of some of these aspects with emphasis on what happens at low latitudes. First, all the phenomena that I showed before occur at very different timescales. So it is important to realize that to observe these phenomena, we need to look over long timescales. So here on this blue horizontal scale, you have a time scale, scale of time constants, which goes to about 10 to the minus 8 years to seconds, minutes, hours, day, year, century, hundreds, thousand centuries, and finally hundreds of billions of centuries. So all these stages are relevant in terms of changes occurring in the upper atmosphere. And also, I will take the same code as before to explain how the different phenomena have their imprints on the upper atmosphere at different timescales. So first, for the space environment, what I call space weather in red. So the effects of the IMF changes of magnetospheric substorms and storms, when they occur at, let's say, seconds to minutes to hours and days. Okay, so it's here. The changes in tides and cosmic ray radiation induced by solar cycle and solar activity, they are something that goes to, let's say, the yearly or multi-annual timescale. And finally, the changes in the upper atmosphere induced by astronomical changes, so the Blanc cycle and so on, they operate at tens to hundreds of thousands of years. If we go to the blue, which is the atmosphere also affects the upper atmosphere. The effects of thunderstorms via electromagnetic emissions, electricity charges, and so on. They have a broad scale of temporal variations from seconds to, let's say, years because of the seasons. In addition, the changes in upper atmosphere, which has introduced by anthropogenic climate change, as we know, go from decades to centuries. So finally, solid Earth. So for solid Earth, of course, we have the effects of earthquakes, which are from seconds to minutes or hours. We have the effects of volcanic eruptions here, which are from days to years. And we have the secular variations of the geomagnetic field up to the dipole reversals, which can occur between centuries to hundreds of thousands of years. So that's the whole temporal spectrum of all these phenomena we want to study, to tell you that to build an observing system like the IMCP, we need to build something that will last over at least several years or rather decades. So it's a multi-decadal effort that I think we should try to initiate if we want to take the IMCP concept seriously. So with that, I will go through, let's say, some of the phenomena. Basically, here we have a summary of the different phenomena and how they affect the globe in terms of latitudes and longitudes. So for the solar wind, for geomagnetic variations, well, this is really organized in terms of geomagnetic coordinates or geomagnetic latitudes, and that's why I show it here. It's one first reference frame we have to cover, the geomagnetic latitudes and longitudes. For the atmospheric phenomena, greenhouse gases, atmospheric waves, you have here a map of the surface direction and intensity of winds in the troposphere, which shows essentially that circulation is zonal, the average circulation is zonal, and there are very strong contrasts between the ocean areas like the Pacific here and the land regions like Africa, Asia, and the Americas. So we have in the system to cover this contrast. In terms of atmospheric electricity, this map here to the lower left shows the world global occurrence frequency of the thunderstorm phenomena, so the number of strokes produced by the different thunderstorms. You see that the maximum is here in Africa, in Central Africa, with additional activity regions in Southeast Asia here and in South America. And finally, if we look at the seismic activity, it is essentially over and along what we call the circum-Pacific fire belt. Of course, as you know, it is very intense, particularly on the east coast of Asia and on the west coast of the Americas. So those are the considerations we have to make to deploy an observing system that will capture the different phenomena that are mentioned here with these labels. So the IMCP is based on actually defining two main great circles along which we could preferentially deploy instrumentation. So as a continuous red circle, you have what we call the main great circle. So this one runs along 120 degrees east and 60 degrees west. So across Asia, essentially, China, Southeast Asia, Australia, and on the other side of the globe, through the west part, the east part of North America, and through central South America. So with that, you have essentially a first meridian that will capture most of the phenomena because it goes not far from the geomagnetic pole, and therefore it will capture both the latitude, geographic latitude and geomagnetic latitude variations. Then if we want to capture the other phenomena, we need to add a second meridian in quadrature, and that's the idea of the concept. And this one would run through 30 degrees east, so through Central Europe and Central Africa, more or less, and on the other side, through Alaska and Central Pacific, not far from Hawaii and not far from the French Polynesia. So with the combination of these two great circles, you see that you capture most of the phenomena. Seismic activity, more or less along the Circum-Pacific fire belt, and the main and the most important area of thunderstorm activity to study all atmospheric electricity phenomena. So that's how we came up with this concept of deploying the IMCP, the International Meridian Circle instrumentation along two great circles in quadratures, the 120 degrees east, 60 degrees west meridian, and the 30 degrees east, 130 west meridian. So let's go into a little bit now what kind of phenomena we want to study with the IMCP, of course. And I will start with, let's say, what we can call classical space weather. So the coupling of geospace to the solar wind and to interplanetary space. So this is a well-known cartoon when you have the Dungy open magnetosphere. So you imagine here you have in a situation of a southward IMF, the magnetosphere is open to interplanetary space. There is transport of plasma from the solar wind, accumulation into the tail, and then closing back of the convection system towards the sun. So what is important is that the flow of energy is represented here. You have an entry of solar wind and energetic particles plus the solar wind energy. So you have regions of entry of energy and transfer, essentially through the magnetopause and into the tail. Then from the tail, where you have energy storage in the case of in the form of magnetic flux, you have transport of the energy to regions of storage, which are essentially the magnetotail itself and the ring current. And finally, you have regions of energy deposition and dissipation. And I would say that the main part of them is here. And so it's this upper atmosphere and ionosphere in which we are interested. So if we go in more detail towards the Earth, well, it's a well-known cartoon here, you can distinguish the process of how the upper latitudes are going to affect the equatorial latitudes in different steps, which I have identified here. The first one is that as the convection electric fields vary across the polar cap, you have a penetration to middle and low latitudes of the electric fields produced by the ionospheric closure of feeder and currents. You see the feeder and currents here. So this current system extend and tend to go towards low latitudes. Then the second step is the ring current reacts and tends to shield the lower latitudes from the effect of the applied convection electric field by a polarization of the inner edge of the ring current. This has been studied for many years and also modeled, but it's difficult to observe in practice. And finally, you have a generation of latitudinal Hadley cells. And so the neutral air comes in now, because as you are heating the upper atmosphere here at high latitudes, this heating drives Hadley cells, which are going to drive neutral winds towards the mid-latitudes and equator. That's something I have been studied at the time of my PhD, and that was the origin of the Blanc and Richmond theory of the disturbance dynamo. And finally, all these phenomena converge to a transmission of westward flows to the ionosphere and plasmasphere by this disturbance dynamo mechanism during long-lasting storms. So to summarize, the Hadley cells, which are driven by heating of the upper atmosphere at high latitudes, drive Hadley cells, and because of the Coriolis effect on these Hadley cells, they generate westward neutral winds, and in terms, the westward neutral winds drive the plasma into westward motion. So that's the mechanism we studied, and what is interesting is to know how it is translated at the equator. And so this is the next slide. The low latitude phenomena, they are strongly affected by all that happens at higher latitudes. And this is a very simple cartoon of what happens at the equator. So you have along the equator, let's say, an eastward electric field or westward electric field, which drives the currents which are particularly intense along the magnetic equator. The associated electric field, which is into or out of the page here, drives the field lines up or down. For instance, for an eastward electric field, field lines are driven up. For a westward electric field, they are driven down. So with the equatorial associated electrojet current, you actually modulate the vertical motion of magnetic field lines at the equator and the plasma, which is embedded into it. So this is the origin of what we call the equatorial fountain. And this fountain is sort of fantastic amplificator of all that happens at higher latitudes in terms of transmission of the ionospheric electric field. So this equatorial electrojet and what we call the ionospheric fountain, you can see they are driven by variations of the zonal ionospheric electric field, as I explained, but also by the effects of traveling atmospheric ionospheric disturbances coming from the two poles and crossing there. By cross-equatorial winds, you can imagine that there are winds driven across this region from the north and from the south. And it is important to quantify the time response of the equatorial electrojet, of the vertical plasma drifts, of the subtropical trace of the anomaly that we see here in these CHAMP observations changing with time during the major magnetic storms, of the equatorial irregularities which are produced by them, of the spread F through the diversity of magnetic storms. We know there is a considerable amount of literature on this subject. It is a very complex subject. And what is interesting is that it has different expressions, we believe, at different longitudes. Hence the importance of having a global approach to this phenomenon. Just to give you an idea of the average variations at the equator. So here is the behavior of the vertical drifts at the equator, or equivalently the east-west electric field, as shown by measurements of F-region plasma drifts over Arecibo region. So you see that basically the drifts are upwards during daytime. They have an enhancement after sunset. They are downwards during nighttime. So what happens during the storms? Basically, the direct penetration electric fields, so the fields which propagate due to the magnetospheric convection directly to low latitudes, they tend to amplify this phenomenon. This is this study by Senor and Blanc in 1994, where we calculated the changes at low latitudes induced by these electric fields. And you see that basically, well, the electric fields are amplified on the day side and negative on the night side. So they go in the same direction as the average variation. But when you take the disturbance dynamo, and this is another study I did during my PhD, basically what we find is that direct penetration electric fields act to enhance in the same direction the daily variations, the regular variations, and the disturbance dynamo works oppositely. You have it here with the dashed line. So the disturbance dynamo, when it is established via the effect of the Hadley cells that I described before, tend to suppress the regular variation and sometimes to reverse the sense of the fountain. So diminish the crest, diminish the post-sunset enhancement, and so on. So what makes it complex is that the interplay of a penetration electric field and the disturbance dynamo is a function of storm time and intensity, and more or less each event varies in terms of its expression at the equator as a function of storm time, probably also as a function of latitude and longitude. So with that, let me go to another subject of high interest, which is what happened at lower altitudes, where in the tropospheric weather, the situation is not more simple, in fact. You have here this nice cartoon which shows the regular variations of the wind circulation in the troposphere, just to tell you that one thing which is really specific of low latitudes, of course, well known, is the intertropical convergence zone. So let's say essentially the easterly winds converge at the equator. They feed convection at the equator with upward flows of neutral air. And then this upward flow of neutral air, let's say the equatorial chimney, generates Hadley cells, which redistribute the winds and heat towards lower altitudes. So this band between plus 30 and minus 30 degrees of circulation driven by the Hadley cell is what is of interest to us. Of course, for our low latitude studies, it is something very specific. This is the average representation, but for instance, climate scientists currently question how is this going to change with the evolution of climate? Are the tropical zones going to expand, for instance, or to contract? How is the Hadley cell system going to be affected by climate change? We don't know. And in the same way, these very intense weather systems which are produced at the equator, of course, generate atmospheric waves, gravity waves, also longer period waves, which propagate to the upper atmosphere and also are going to change the ionosphere. So second aspect of the low latitude phenomena, what happens in the troposphere and how it is propagating its effects into the upper atmosphere. And here we have exactly this same approach, which shows the vertical coupling in the atmosphere via atmospheric waves, in particular generated along the equator and in the tropics here, is going to produce gravity waves, excite tides, of course, also planetary waves. And part of these wave systems are going to break upwards in the mesosphere and even in the thermosphere, and to produce disturbances to the upper atmosphere. So there is a broad spectrum of atmospheric waves which are generated by the latitudinal structure of the general circulation. They propagate upwards, they reflect or refract at critical levels, and deposit momentum and energy. How all that works in detail, we don't know exactly. Well, of course, it's a subject of intense study and of very high interest, and we should work together to understand all that. Finally, second aspect of low latitude tropospheric phenomena, it's a thunderstorm activity. We showed before here, it maximizes in Southeast Asia, in Africa, and to some extent also in the Americas. And what is of interest to us in particular is the fact that above the thunderstorm systems, you have electric discharges which connect directly the troposphere to the ionosphere conductor. They generate electric currents, but also quasi-static electric fields that accelerate particles. They generate electromagnetic emissions, and all that, of course, is part of phenomena that we want to understand and which all have an impact on the upper atmosphere. Now we'll come to the secular variations of the geomagnetic field. Well, as we know, the magnetic field is varying with time. The magnetic field produced by the dynamo of our planet. You have here in this cartoon, a presentation of the variation with time of the location of the geomagnetic poles. This is the north geomagnetic pole. We know it is drifting with time. It has been drifting regularly since 1980. We can follow it and actually going away from the American continent and towards the European and Asian continents on the other side. At the same time, we are in a region where the dipole strength is regularly decreasing. We don't know for how long it will last, but of course, this also has implications on how the upper atmosphere is coupled to the solar wind. When you look now at the intensity of the magnetic field as a function of location on the globe, you see that if you divide, you do the difference between 2020 and 2014 to see what are the variations. You see that these variations are quite significant. They are particularly significant in the region of the South Atlantic anomaly. And here in the Indian Ocean and over the Asian sector. So all that shows that even the anomalies are drifting with time. And this is going to change the landscape of our upper atmosphere. So let's go to conclude this science part with these effects of these long-term changes on the upper atmosphere. So what we know now is that the upper atmosphere is sensitive to a combined effect of climate change and geomagnetic field secular variations. This is illustrated in these two diagrams. So this one is from Jan Lastovica. It's a classical study that he did about 50 years ago, where he showed by looking at ionosomes that the long-term trend in the upper atmosphere is a slight decrease of thermospheric temperature and a variation of the E layer and F layer. The F layer tends to increase, the E layer tends to go down and decrease a little bit. So you see all of the parameters are changed by the global change of the climate system. In more recent studies, in particular by Kate Nossen, this one, and also other studies by Nossen and Astrid Mote, they showed that the combined trend of geomagnetic variations and changes in the upper atmosphere produced by climate evolution has strong effects. So you here, for instance, have something which is the variation between 2015 and 2070 projected of the total electron content in the upper atmosphere. And you see that, again, in the region of the South Atlantic anomaly, there are going to be strong effects. And globally speaking, the TEC tends to decrease more or less along the equator and at low latitudes. And this has to be monitored. We see also by the variation between the black and the white curve that the deep equator is also moving. So, of course, this has very important consequences on the behavior of the upper atmosphere at low latitudes. So let me tell you now about how we see the geographic deployment of the IMCP and how it is going to respond to our needs in terms of observing all these phenomena. So, as I explained before, the IMCP concept is based on the deployment of instruments along, let's say, two great circles. So, of course, not exactly the great circles, but let's say that there are longitude bands along which we propose to focus observations. So the first meridian circle, this one, in brown, goes along Asia, Australia, and the Americas here. So 120 east, 60 degrees west. And it is complemented, in our view, by a second circle, this one. We call it Europe, Africa, Pacific, which is around 30 degrees east and 150 west, running across the Pacific. So what are the properties in terms of observation of these two circles? First, this is a cartoon which shows that our Chinese colleagues have deployed a specific observation system on their own, let's say, country, territory. It is a set of two crosses with intense observations and lower, let's say, lighter instruments that cover the Chinese territory, but also cover observations over the two poles. So this Chinese Meridian project is sort of the template of what we want to do for the whole IMCP, because it shows how we can combine light instruments, network instruments, and heavy instruments to monitor the upper atmosphere. So, first meridian circle. Well, first, thanks to the Earth's rotation, if you look at how it is going to span local times, well, such a circle just by itself is going to cover all local times in 12 hours. So it's a first merit, it's basic merit. Every 12 hours, you have a full coverage of all local times on Earth. In addition, it fully covers both the magnetic and geographic latitudes because it basically goes through the geomagnetic poles. It maximizes continental coverage, and that is, of course, convenient for the deployment of ground-based instruments. So in that sense, it is optimal. And finally, it gives a good coverage of the circum-Pacific fire belt to study and monitor earthquake effects. So just by itself, this first meridian that we call the prime meridian does all that and can already address all the main phenomena that IMCP wants to study. But if we add the second meridian, then in complement to the first meridian with two meridians and the rotation of the Earth combined, you can cover all local times in only 6 hours. So it is, of course, much more powerful, in addition to the fact that the longitude coverage is much better. It captures the land-ocean contrast and the world maximum of thunderstorm activity. World maximum of thunderstorm activity, as we show, it is in Africa. And the land-ocean contrast, because it compares a continent coverage of Europe and Africa with a cross-Pacific coverage, where, of course, deployment of instruments is difficult, but we have the possibility to capture these effects, which are certainly important. And finally, as I just said, it gives a specific coverage of the ocean hemisphere. So that's the idea for the deployment geometry. And now let's focus on the low-latitude phenomena. So I would like to mention here some of the challenges that the IMCP can address at low latitudes, and we can discuss that later, and show why the IMCP is very relevant for low latitude studies. So first, space weather. For space weather, of course, the equatorial and low latitude effects of space weather, and in particular of magnetic storms and substorms, are very complex, and they are amplified at low latitudes. So we want to understand them, of course. They are particularly important. In particular, the zonal electric field and the electrojet current, how they behave as a function of storm and substorm, how they react to interplanetary conditions. The zonal and meridional transequatorial thermospheric winds, how they combine with the effects of ion drifts. And finally, how gravity waves generated on large scales by auroral heating propagate from the auroral zones to the equator. All that is open questions. Second area of research, tropospheric weather and vertical coupling. There are specific effects of tropical weather on the upper atmosphere that we want to understand. How the Hadley cell that I showed before specifically generates waves, gravity and planetary that affect the upper atmosphere. How does the intense thunderstorm activity, which is characteristic of low latitude, propagate upward, and what are its effects on the ionosphere? Third area of research, geomagnetic field variations and climate change. The effects of the drift of the deep equator and magnetic anomalies combine, as I showed, with specific effects of climate change at low latitudes. Change in the tropical zone, which we don't know how and when. Access of greenhouse gases to the upper atmosphere. How does it work at low latitude? Are there specific phenomena? All that, of course, needs to be studied. And finally, well, the longitude variations of all these phenomena are, I think, not very well known, and they are significant, and therefore they need to be studied. So here in this slide, I show on a map of the Earth, this map of the deep latitudes. And you see in green here, the current location of the deep equator along which these equatorial phenomena maximize. So you can see that with the deployment of IMCP instrument over the different continents, we have at least already, with the two meridian circles combined, 3 regions which we could call regions of intense low latitude research. One here is of course, the Southeast Asia here, going, let's say, from the tip of India to this region here. Of course, this one is covered by the first great circle. The same great circle can also cover the traverse of South America by the deep equator and the equatorial electrojet. So second area of intense research that could be coordinated within the IMCP. And now with the second meridian circle and the contribution of our African colleagues in particular, we will have the possibility of covering in depth low latitude phenomena over Africa. And let me mention here that Africa offers the longest continental traverse of the equatorial electrojet and of the low latitude region of the ionosphere in the Earth system. So if it's a place where deployment of instruments along the equator is, and across, of course, the different latitudes to the tropics will be extremely important. Ideally, we should also be able to deploy instruments in the Pacific. We have to find the correct islands to do it. It's a little bit more difficult, and also to develop marine research to do it. So altogether, 3+ regions, 3 or 4, are offered by IMCP for intense low latitude coordinated studies. And just by working together between these different regions of the world, we can have access to the poorly known longitude variations of all the phenomena I discussed before. Just to mention the case of Africa, or to which you are maybe less familiar, Africa is already offering a significant deployment of space weather instruments. So you have here the location of different GNSS receiver networks over Africa, South Africa, Central Africa, also in Algeria, here another GNSS network. You have a network of magnetometers. You have at least one Fabry-Perot interferometer looking at thermospheric neutral winds, which is currently deployed in Morocco here, where I spent a good fraction of my young ages, by the way. And finally, in Nigeria, they are now developing an HF radar that will look at drift intensities of the ionosphere along the equator, and will be in a fantastic position to study equatorial phenomena. So you see that there are opportunities for collaboration already, and I'm sure with the development of more instruments in Africa, it will be going better and better. So IMCP observation system and low latitudes now. So to summarize, the two great meridians together offer three regions of intense low latitude science: Southeast Asia, Africa, and South America, plus possibly observations in the Central Pacific. Of course, they could and should perform under the umbrella of the IMCP coordinated observations and data analysis campaigns under the four themes I mentioned before: space weather, atmospheric weather, climate, and their coupling. And of course, I'm not necessarily comprehensive. There may be a lot of other very interesting ideas that I did not mention and did not think of, but it's for everybody to contribute here. These coordinated observations along the two great meridians naturally provide already critical access to longitude and intercontinental variations at low latitudes, and they sample regions with different shifts between geographic and deep latitudes. In Africa, the geomagnetic equator is to the north, same in Southeast Asia, but in the Americas, for instance, it's the opposite. So we can also see how the latitude variation between geographic and geomagnetic latitude affects the phenomenon. And finally, it is particularly interesting to notice that since tropospheric convection in the intertropical convergence zone is centered on the geographic equator, whereas the ionospheric convection, what I call the fountain, is located on the deep equator, exploring how the combination of the two changes when the relative location of the two equators changes is something very interesting to study the complexity of the process and the complexity of the upper atmosphere at equatorial latitudes. And that's something that basically the IMCP make it possible to study. So my last sentence is my provisional conclusion. I think the IMCP is really a great tool for low latitude research. And I am very happy that I've been invited to this seminar of the AOGS-RAC Low Latitude Working Group. And I really look forward to working together hand in hand and between the different continents. So thank you very much. And I'll be very happy to answer questions.
Yeah, thank you so much, Michel, for this lecture. Next week, we have AOGS in Singapore, and some of us will meet there also. And I mean, some of the working group members, including, I see that now that I think that Professor Aisha Liu, are you there? Aisha?
Yes, yes.
Yeah, can you turn on your camera so that you can meet the Michel, because you two will be the leading light of the WG working group. Yeah.
Yeah, wait a moment, please. Sorry. Can you see? Yeah, okay. Hi, Michel.
Hello,
very nice
yes,
presentation.
Very nice to meet you.
Nice to meet you.
So I hope that in Singapore you can find time to talk to each other how to organize the working group. Yeah. I think I will let Aisha to introduce yourself to Michel later, in Singapore. But I have a couple of questions. Anyway, anyone have questions now? I mean, please raise your hands or just ask, turn on your mic and ask Michel the question. Maybe Aisha, you have questions?
I don't know. I just want to ask a question about the data availability. If we want to use this data from these three chains, so we need to apply for access, or or is open?
Well, yes, the IMCP is, of course, associated with a data system that distributes the data. And as far as I know, the model is a CMP. And basically, you register and you go to the database and you can work on the data online. So I will actually circulate the information about how to access the data which exists already. But for the development of the system, I think we anticipate to have several data systems around the world working together to amplify the distribution of data and facilitate access to the data by all interested participants. Actually, not only the data providers, but whoever is interested in analyzing the data. And I have in mind the idea that the IMCP could evolve. Actually, I think it's the plan of our Chinese colleagues into a sort of advanced study institute, in a way, in the model of the EC system, which it knows very well, where international teams could meet and work together to use data based on a specific science question. That would be the model. So we need first build the observation systems that it deploys the instruments, make sure they operate. In Africa, for instance, there is a significant problem of maintenance. We have to address that.
Yeah, I see.
Then, of course, after that, make the data available. So that's a question of access of data. And it has to be free access. I mean, it's a current trend in science. And then the upper layer would be an institute where you could really formulate questions, make scientific projects, and work together internationally.
Yeah, thank you. Yeah, indeed, this is a really brilliant, brilliant plan and infrastructure. Yeah, for scientists collaboration.
Yes.
Yeah.
Yes.
Thank you for your presentation again. Yeah.
Thank you very much
yeah,
for the question.
But Michel, the IMCP is not yet a real project, right? I mean, it's still to be launched or what?
Yes, it was currently actually going through competition for international big project in China. I know they have access to the final stage of the selection, and we should know more soon. Yes. So the CMP is still working, and it is working informally via collaborations between different institutes. But yes, the big kickoff, let's say, is still to come.
I mean, from my point of view, you might be, since you're close to the people there, it might be useful to propose to have some pilot project, like IMCP, but the IMCP pilot project to allow build up some expertise and experience in data sharing among your group and also the low latitude, whoever interested.
Yes, yes.
And
yes.
you can maybe Haisha could identify a couple problems so that that the people are interested could share the data and I mean, like a virtual science team for now without waiting for too long. Yeah.
Yeah, I agree. So it would be it's a good way to start, yes, because it will make a concrete step forward. It's yes, very good suggestion. I will convey it to my colleagues. In fact, when I will be in Beijing in 2 weeks. Yeah,
and from that point of view, it would be good to tell people what kind of data are available. Because I mean, what kind of instrument and what kind of data available that people can use. Of course, they can go to web page. Other thing, of course, is that you want to involve more institutions who want to join IMCP but want to contribute to the data taking.
Yes.
And what kind of instruments, what kind of measurement you would like them to have to contribute to.
Yes.
Yeah.
Yes. Yes, I agree. Yes. So we should.
I mean, in particular, we are, because of AOGS, we are interested in the institution researchers in Asia and Oceania. Then they just happen to be in the low latitude region, and then they would like to learn to have some ground-based facilities, and that you might be able to help them if you could. And because I spoke to Professor Yajun Zhu, you might know him, a month ago, and he said that they could even support some ground-based facilities, instruments to people who might be interested.
Yes. So actually, since we will meet some of us at the AOGS next week, we could prepare with the Recherche some information about what instruments are already available, how to access, and so on, and exchange with the community on this. And
if you have questions, you raise your hands, or you just turn on your mic and questions. Give us questions. It's a good opportunity.
Yes, and I see some of our African colleagues are there also. So maybe they.
So Jocelyn, Porte,
yes.
You have questions? Oh, we cannot hear you.
You don't have your mic is closed. Jocelyn, your mic is closed.
I said I have a question. I have a question. I listen to you.
Oh, okay. Yes.
The other thing I want to ask is that you did not mention about the possible, the importance of spacecraft measurements, satellite measurements, projects like ICON or like GOLD or like Cosmic 2.
Yes, well, I didn't, and of course, because the IMCP is a ground-based project, but you are absolutely right. I think it's absolutely essential. I think I was at the CEDAR workshop in the US at the end of June, and it was striking how much synergy between ground-based measurements and space measurements are important. So yes, we need to associate the IMCP with a space program that basically covers the same types of phenomena. Yes, and you are right, ICON, GOLD, also ROCSAT, I could have shown the ROCSAT observations are very important and CSES also in China, are very important to do the type of monitoring as I described. So you're absolutely right. Space is critical.
Right. I think you agreed, right? All right, good. Any other questions to Michel? I think that it's 5:05. I think that there is a very nice detailed lectures, and I think we'll have more chance to. I think that in future we would ask a few more experts on this topic to give lectures, and I'm thinking of asking Madame Amori. And,
yes.
I haven't written to her yet, but I'm sure she'll be happy to. I'm
sure she would. Yes.
And then I will ask you for a couple more names, to add to the lecture list. Yeah. Then we would finish this session now, and then I want to say thank you again to Michel, and then I believe this will be the beginning of a dialogue between the IMCP and the low-latitude. I think that way that we have almost like a 3D coverage.
I really look forward to it, and I think our colleagues also. So yes, yeah. Let's keep in touch, and we'll see you in Singapore for summers next week. We can discuss more.
Okay, great.
And thank you again for the invitation.
Let me see. There's just to thank you. All right, Michel. Thank you so much. See you next week.
Thank you.
Yeah. Bye bye.
See
you next week.
Bye.